what we'll be doing. Now, the method is, there's a new technology, it's an instrument now that allows us to measure the eye, and it gives us all the curvatures and their measurement on each and every point. So that machine will use it, and then it can plot something like this. For this person, it's how it was showing exactly. This is the anterior part, and this is the posterior. So we took several measurements, wanted to see the behavior of the eye of what is happening. And after those measurements, this was one eye being measured, and these are the 43 measurements, and they are so scattered. And if the eye was behaving or was stationary, there should be only 1 point, which is different now when we check the back surface of the eye. This is the front. So there are many variations. While this on the inside, there are less variation because this is the back surface where now the homeostasis of the eye is constant in comparison to the outside where there are many factors happening. So from all those 43 measurements, we use this formula to calculate the powers now. We calculate the power based on the radius and the refractive index of the eye. And this is the statistics now on how we'll be able to communicate with statisticians and scientists and engineers and anyone. So the power is written in the clinical format. This in optometry mean only 1. But now here we're able to divide them individually. Those who are in mathematics, I'm sure they know a lot of Hamiltonian matrix. That was someone who was just going to a conference and somewhere did not have a pen and anything. He decided to write this I, J, and K on the bridge while the cement was still. And then when he came back, he found everything and remember, because it just came when he was just near the bridge and he managed to write everything there. And then he gone and he came back and found everything in there. So now, based on those measurements that we did, using the scientific way, we are able to see how much the eye is changing, both in the front surface and on the posterior surface here. Or there's so much changes that's happening here on the front than when it's happening on the posterior surface, at the back surface, there the homeostasis is bad. But even though when we look at the diagonal one, these are the variances that are happening, and those are the covariances. So we can also ignore what's happening here below this diagonal line is the same as what is on the other side. So it's showing how much the way we see it keep on changing. Now you might see something looking red, pinkish, something. Things keep on changing in between as we are looking through. And then now, the cornea. If you look in one's eye, that black part that you see, it's not the cornea, it's the iris. The one that is reflecting in front is nearly equal with the iris. And then hence we say that black part you see is the cornea. So I've got a thickness of 0.5 millimeters. Because of that thickness, so we look at how light rays is traveling from outside, coming into the eye. And then the T, that A, B, C, D, is what is happening in between that thickness and what goes out when it gets out of the cornea and is going to the retina. So the state of how we see is like this, the operator, the transference, and the state of light coming into the eye and how it gets out of the cornea. So in future, we'll do it for the whole eye, but now it was on the cornea. And each one of these states is, we can represent it in this Y1 and I. Because when a light rays come into your eye, it comes at a certain position, which have got vertical and horizontal. And there's an angle, which have got both vertical and horizontal. And then now, that's where we try to show it. Then, we calculated the transference. And when we calculate the transference, we calculate from the back, from the right. In physics or optics, light is always assumed to travel from left to right. So we calculate in reverse to go and find exactly what is the total transference of the cornea and the divergences of what's happening. And now, the word symplectic is so much common in physics. So, because the transference is not symplectic, it means we cannot do any calculation inside. We can't do any multiplication on it. So now, we have to go and transform it into a form that will be able to do the calculation and all the calculation and the mean. So sorry, I'm going too far. So we have, from all those 43 measurements of the transference, we have to convert each and all of them. We calculate the logarithm of each. Now, it's easy to calculate a part of the eye and find the average of it. But this is the method that will work to find the average of the vision of how we see. Individual part we can do it, but for the vision. And hence, we use the logarithm to convert it from the ray transference into the Hamiltonian matrix. And that Hamiltonian matrix is, we find the logarithm of each of these. And when we come and get the logarithm, that A with that head there, it's part of this, it's part of this, and part of this. So in this A, I've got part of all of this one into this one. And now, once we have it, then we have got a vector space where we can do all the calculation. And this is just a representation of expanding of how the A with the heads on top, how they come about more mathematical. And sometimes, when we convert into the Hamiltonian matrix, we can also work in a vector way. But this vector way is a challenge that it's not able to draw a three-dimensional, because this vector have got 10 points on it. So we have to, it means we are unable to draw all points which will be 90 degrees away from each other for all of this one. So mathematically, we can do, but graphically, it can't. And then now, we can cut, that's how we get the mean coordinated vectors. This mean coordinated vectors is similar to the final mean of the Hamiltonian matrix. And then now, these are the variances. And all those numbers, hence they are all in there. It's because the cornea is so thick. Now, once we get into the eye, it will start to show us how those numbers, as they have got negative numbers and some, there are numbers that go beyond there. And then now, this is the mean Hamiltonian matrix, where we can do all the calculation of anything about the eye on how we are seeing. But now, when we finish doing all the calculation, the ray transference, we cannot do calculation, and hence we convert into Hamiltonian. And once we convert, then we start to do all the calculation. And when we finish doing the calculation, we must convert back to the ray transference, the normal physical light that's coming in there. And to do that, we use the exponential function on the MATLAB or new technologies that will develop. And now, once we have this, now, from this person here, because these numbers are close to 1, all of them, that is A, and this is B, that is C, and this one is D. This one is showing how far can we see. Because it's close to 1, it's closer to identity matrix, and now it means that person is hyperopic. You can see very well. Once these numbers, this one and this one, now they've got negative numbers. Now they mean your short-sightedness. But the thickness, hence here, still remain the same for that object. And now, this is the divergence of the light that is coming onto the cornea before it's sent into the brain. The divergence is, if we switch off everything here and we close and there's no light, we are not going to see anything. Until we go and put a spot of light there, all of eyes will start to go there. Once completely darkness. So whatever comes from that light, whether it's natural or artificial, it goes as a vergence. If you throw something in water, you see those wrinkles going around. That is how the light rays, as it's coming to the eye, it's appearing to be. And then we draw this. And this is where we're interested so much on the end result of what will happen. This, whatever is happening, is in that 5 by 5 matrix, everything in. But the exciting part of it might work now, it might not work, or in future. We're able to find that there's this point in here. If this person was unable to see for any reason, we can manufacture an artificial retina or a biotic retina, and we go and put it in the middle of the eye, and after putting that, we'll need to put the spectacle power of this one, and we are able to connect those wires to the brain. We use this part of the brain. We are able to connect them. That person will be able to see. Might take long. One day it's coming to happen. So that's how now the average eye, we cannot take all of your eyes and we try to put them. Always in research, we want the average. But in the case of a vision, because the vision goes in hand with the brain, so we cannot add all of you, but you need to calculate individually, average eye. Thereafter, we can go and take all of our eyes together and put and see how the variation is happening in there. For those who are mostly in mathematics and statistics, okay, the method that is you're using here, it's not going to work if there's a negative engine vector. So we ask those in mathematics what it means, because it involves some vectors and the vector space in there. But fortunately, from there, the future research is going to go into the Euclidean vectors now, where we are going to show the whole eye as a whole, calculating on it, and then showing exactly, because that is the end result. At the moment, we can change the heart, can change kidneys, but we can't change the eye. If that was possible, we will be accept this cornea. We can change the cornea, we can remove the lens and put an artificial, but the retina, where transduction is happening, from there, nothing can be done. And hence, until we come with some new wires or new format that we can put someone's spectacles here, and we put wires that will go directly into the brain. So at the moment, remember, once you go blind, we can't change. Once the kidney is malfunctioning, we can remove and put something else. But with the eye, we can't do anything. So I thank you and for giving me this time and the organizing committee. Thank you.
Okay, thank you, Prof. Matebula. I think for me, I can just wish him some luck as he tries in all his endeavors. I think he really has a job to do. Okay, but let's open this session now for questions.
Oh, need this.
Yeah. I forgot. You can just think there. Use this one. Use this one.
You can also ask about your own eyes.
Okay, thank you. I don't know if I understood you very well when you were explaining those numbers, those matrix numbers. So you mentioned that those ones with negative signs indicate that you are short-sighted. So I want to ask is it possible for all those numbers in the matrix box to be negative? And if that's the case, what does it mean in terms of being short-sighted?
Not all can be negative. There's a thickness that will be positive. The only part that will be negative is this one. If you go to an optometrist, they put something, letters there that you read to check. That is the only part that can be negative if you can't see them, where now you will need some negative lenses. Because negative lenses, what they do, they diverge the light, and hence that negative is coming from.
Thank you for your presentation. My question is about the eyes and allergies. For me, since you said we can ask about our eyes, during springtime when the plants are, I get allergies. Some people, they call it high fever. Then my eyes will be watery. So can you please tell me what will be happening?
I think even Prof. Mohanedi could help in that hypersensitivity thing and allergies. Okay, allergies are so difficult because there are people who are allergic to their own families in their house. So you have to check how are things in your house. Are they clean? You find that you have got dogs, you have got dust. In your house, you have got a mat. So something. So the only way, somewhere around May, June, before we get into September, please go and consult. They will give you a certain medication that will try to prevent you if it only happens during September. Find out whether maybe it's the heat and the dust or now the new pollen that's coming.
Oh, okay, you answered my next question about the pollen. Thank you.
I think it also speaks to systems thinking, dynamic systems.
Thank you very much. It's good to see you again. I once came to the clinic at the university, and then I wanted to test my eyes, just out of curiosity. So after testing, they put some liquid in my eyes when they were testing. After that, I couldn't see the text in my phone. So I want to understand what was the problem there, because before I could text, but after that, I went straight to sleep.
Please don't misquote me on this one. At the university, we are training students. Okay, we examine, we do everything. So on the day when you came, if you look inside on this black part of the eye, there's a small hole in between. So when they put that medication, they wanted to open so that they can see clearly the inside of your eye. So they were investigating the inside of your eye. So there's a medication. So that medication, what's happening, it locks the ciliary muscles. And when it locks the ciliary muscle, you can't see because it dilates the eye. And more aberrations, more disturbance on your vision is happening. So hence, after sleeping, the metabolism will slowly remove that medication through the blood flow. Slowly it will go away and then you will start to see again. It might take a little bit. Normally, it takes time for people who with dark skin because of the melanin.
Okay, let's have the last one.
Thank you so much for quite an interesting presentation. I have just a general one. Realizing that much of the presentation is statistical and mathematical in nature. Have you perhaps come across the attempts to represent those equations, but with taking the advantage of machine learning? Because machine learning itself, it's largely statistical. And I'm saying this on the basis that the comment you made to say there isn't a software that was available to perhaps model or handle those equations.
Thank you for that. I think, yeah, maybe that's the future way to go, and hence I'm happy that the organizers brought me here. Possibly the physics department and optics, we might see something now that we can go and start to work on, because so much of this is physics and optical engineers, because that thing, the bionic retina, it needs really physicians and physics, and I'm hoping it might happen next week. Maybe the mathematics that I'm doing can stimulate some of you to come with something that will work better, and then we move away from this. Okay, that one you did, it did not work fine, but then we can use this one. So many things will start to come now, and hence I came here because I'm an optometrist, so optometrists don't understand this, and all the papers have been rejected, so they need to go perhaps to statistics or mathematics. Thank you.
Thank you so much.
Just one more.
Oh.
It's just a comment. I think
I hope.
I'm sorry,
the
Chair.
last one.
The significance of the question that was asked here now, for me, because we cannot leave it unchecked, it's not necessarily the response for me. It's what possibilities are there for collaboration within our university, within the faculty and other faculties, because he comes from the health sciences, obviously. But I think the question, if we look at the profile of the person who asks the question and where he finds himself in, there's quite a lot of exploration that you need to do with the team, with Professor Nwebe, about exactly what you were talking about in terms of the innovation that you want to come up with, should you come up with innovation in terms of doing modeling of materials and testing the what is that? The numbers, the statistics there, if they can be put into, perhaps maybe visualized in a different way. So I would encourage that out of this talk, maybe they should start having some conversations.
Okay, thank you so much. We do appreciate what Dr. Mavila is saying. Of course, everybody, I think you have listened, and there is really a room for collaboration. So I think, as Prof. Matebula indicated, the mathematicians, all those who can come on board, maybe then they can discuss that possibility. So we thank you, Dr. Mavila. Thank you. Can we please give him another round of applause? Okay, we will just wrap this session by doing, by simply saying to you, Prof. Matebula, the faculty has actually prepared a token of appreciation for you. So thank you so much for availing yourself, and we will have Prof. Mohanedi doing what she did in the previous session. Thank you.
Oh, thank you.
You can just step down. thank you so much. We can now go to the different rooms. Thank you.